video is on the alternating series test. So what is an alternating series? Some series may contain terms that are both positive and negative. The most common series of this type is the alternating series, where the signs of each term change back and forth between positive and negative. Here are some examples. So you'll usually see an alternating series will have something like a -1 to a power based off the index, okay? And then that right there alternates that sign from positive to negative. It can look like this right here is another one, where it's n plus 1, or you can have n minus 1. All of these are examples of the same kind of thing. And this is also another one. Kind of amazing that it is, but remember the cosine of n pi, and n is a counter, 0 to infinity. Well, this alternates back and forth, pi, 0, pi, 2 pi, 3 pi, 4 pi, and so forth. And so the cosine there is either 1 or -1. So then again, you have that alternating series here. The alternating series test allows us to determine convergence. Okay. First off, the nth term has to be positive. The a sub n expression without an alternating part. Okay, so you want to just basically take that whole thing without the alternating part, and you want that to make sure that's positive. The alternating series, which is -1 to the n or -1 to the n plus 1, okay, converge if the following conditions are met. The limit of the nth term is equal to 0, and the next term in the sequence is less than the previous one. Okay, this means that the values of a sub n are non-increasing because there was an equal sign there. It doesn't, I said it wrong. This means it's not decreasing because it could be equal. Okay, so it has to be less than or equal to the previous one. So non-increasing. Okay, so let's take a look at this and see if we can figure out an example right here. So let's go take a look. So here's our first example right here. Determine if this converges or diverges. So the first thing you want to do is tell me what a sub n is. So we're going to let a sub n be equal everything in here except for the alternating part. So this would be 1 over n. So we got to check our condition. Is the limit as n goes to infinity of 1 over n equal to 0? Yep, and we're good there. Okay. We need to verify that the next term is less than or equal to the previous term. So the next term here would be 1 over n plus 1. Is that less than or equal to 1 over n? And you can do a check here. It is, but you can do a cross multiply check. And so therefore, sure enough, this one is indeed true. Okay, so from those conditions right there, we can say, so by the alternating series test, this sum, and going from 0 to infinity, and going 1 to infinity, of this converges. And there you go. Okay, and a couple of side notes here. I'll let you guys take a look at the notes page that I have right here before we do another example. Recall that the summation of 1 over n is a divergent series because it's a simple harmonic series. But if it's alternating, then it's a convergent series. Okay, so that's something to keep in mind. You'll see this one pop up quite a bit when they do other problems and such. So here is another example right here. Does this series converge or diverge? So our a sub n is n over n plus 1. The limit as n goes to infinity of this, okay, that equals 1. So because it does not equal 0, it fails. So this series diverges. Okay. Let's take a look at some other notes that I have. Alternating series are a little unusual in that they exhibit three different behaviors. Okay, they can diverge, they can conditionally converge, or they can absolutely converge. And we're going to talk about what all those things here mean right now. So here's recall the following two series. So we have the harmonic series, which we know diverges, which is this thing right here, 1 plus 1/2 plus a third plus a fourth and so on. And here's the alternating harmonic series, which does converge, 1 minus 1/2 plus a third minus a fourth and so on. As we keep adding forever, we understand that the sum may continue to grow without bound. For the alternating, we add a number, then subtract, and then add and subtract and so on. We can see why this might converge. So the question that comes out of this is, did this series converge because of the alternating signs, or would it have converged regardless if all the terms were positive or all the terms negative? Okay, so that's what we're looking at. Look at this series right here, 1 over n squared. Okay, 1 plus a fourth plus a ninth plus 16th converges because it's a p series and p is equal to 2. Let's take a look at the alternating form of that. Okay, this will converge because of the alternating series test, and you can see how it worked through that process there. So because both series converge, the -1 to the n minus 1, so the alternating sign, was not really necessary to make the series converge. This wasn't the catalyst that pushed it over the edge to converge. So if a series has infinite positive and negative terms, was it the negative terms that caused it to converge, or would series have converged regardless? This is the concept behind absolute convergence versus conditional convergence. Did the alternating signs make it converge where it would normally not, or would it converge regardless of the situation? Okay, so that brings us to this part right here. So here we have the sum here we have a series. It's an infinite series. If I put absolute values on here, if that series converges, okay, then this series converges absolutely. Okay, if this series converges, but this series diverges, okay, then the original series right here converges conditionally. It converged on the condition that we had both positive and negative terms. That's what it's telling you, conditional convergence. Okay? So, that's the concept that we're looking at here. Let's look at another example. Does this series converge absolutely, converge conditionally, or does it diverge? Okay, so we can go through the process here and we can see the alternating series test on this thing, and we can come over here and we have a sub n is 1 over the cube root of n, okay, which we can write as 1 over n to the 1/3. Look at it that way if we want to. We can take the limit as n goes to infinity of this item, and we see that this right here is going to go to 0, so we're good. Is the next term, n plus 1, is that smaller than the previous one? And for values greater than or equal to 1, it is. So we know by the alternating series test, this series right here, n equals 1 to infinity, -1 to the n over the cube root of n converges. Okay, so we know that. Now, the question is, was it necessary, was this part right here, this alternating part of it, the -1 to the n, was that a necessary part that caused this series to converge, or would it have converged if all the terms were positive or all the terms negative? So that's the question. So we need to look at 1 to infinity, the absolute value of all that. Okay, well, an absolute value just makes them all positive. So that means this is equivalent to this series right here of just 1 over n to the 1/3. Let's put it in the 1/3 format. This, if you didn't recognize it before, this is a p series. It is a p series where p is equal to 1/3. And so since that is less than 1, we know that this series diverges. So it converged over here where the negative ones were in play, and it diverged over here when they weren't. Okay, so that means the negative signs were necessary, which makes this converges conditionally. And there you go. Okay, let's take a look at another one. Does this series converge absolutely conditionally, or does it diverge? Okay. This series here has many positive and negative terms, but is not an alternating series. Okay. The sign of a values turn positive in the first quadrant, then they turn positive in the first and second, then negative in the third and fourth, and it just keeps on doing that process. So they're not all alternating, they're just kind of like in clumps. Okay, but let's consider this. N equals 1 to infinity of this, the absolute value of that series. So this is going to be equal to, since this is squared, we can eliminate that off the bottom. The absolute value stays on the sign, and this is n squared. Okay. N is an integer. N is an integer. So n cannot equal pi over 2. So the absolute value of the sign of n has to be less than 1. Okay, and it cannot equal 1. It has to be less than 1. Not equal to 1. Okay? So because of that is less than 1 for all n, this thing, the sign of n, absolute value of the sign of n over n squared, is going to be less than 1 over n squared for n greater than or equal to 1. Okay? So by the direct comparison test with a convergent p-series, that right there, where p is equal to 2, then this series converges. Okay? and then this thing, the original, over n squared will converge absolutely. Okay. Let's take a look at another piece of information that I have for you before we go into the next question. The alternating series error bound. Okay? If a series converges by the alternating series test, we can determine an error bound of a partial sum approximation to the infinite series. Now that we know if a series converges, what does it converge to? A lot of the time we don't try to figure this out. Most of the time only for the geometric one do we bother. What if we add only some of the terms of this infinite series that converges? How close would that value be to the true answer? Okay, and so let's take a look at some of the things we're going to do. We're going to be using the alternating, we're going to use the alternating harmonic series to explore this. So here's the alternating harmonic. We know this converges. Okay, but what does it converge to? Well, if we add up the first 5 terms, how close are our partial sum be to the true value of this series if we added all the terms? Okay, so let's add up the first 5 terms. So S sub 5 is approximately 0.783. And so is this answer close? Now, what is the actual answer? Can we figure it out? Okay, and so let's take a look. If a series converges by the alternating series test, then the error from using the first n terms of the series to approximate the value of the series is less than or equal to the absolute value of the first omitted term. Okay? So the error is less than the difference between the actual minus the partial, and that is going to be less than the absolute value of the next term in this series, in the sequence. Okay? So let's take a look and see how this plays out in an example. So here's the series. Okay? We just found out that the sum of the first 5 terms is equal to that right there. So this is the same series we were looking at. We use the alternating series error bound to find a lower and upper bound for the value of this sum. Okay? So we know that our error is going to be less than or equal to the absolute value of a sub n plus 1. So for us, that means our error is going to be less than or equal to the absolute value of a sub 6. Well, what is a sub 6? Well, remember, in our sum, a sub 5, the fifth one is 1 over 5. The next one is going to be 1 over 6, so this is going to be less than 1 over 6. And 1 over 6 is equal to 0.16, and the 6 repeats. Okay? So, 0.783 repeating minus 0.16 is less than or equal to our total sum, and 0.783 plus 0.16. So the actual sum is between these two values. So if you work these out, you're going to get 0.616 is less than the sum, which is less than that. Okay? And so that's where the sum of this series lies, between those two values. Now, a little piece of information for you. This series right here is actually, the whole sum is actually equal to, you don't have to know this, I'm just showing you what it is actually equal to the natural log of 2. And the actual log of 2, if you use a calculator, will give you a value of 0.693. And so you can see that this value is in between those two numbers. This is the actual. Okay, some information there for you. So that's the way I can find an upper and lower bound. Okay, I don't see that happening too often. More in tune, they're looking for what the value has to be right here, this error. Okay, so I have one more example for you right here, looks like. So consider this series right here, the sine of 1, which is this series right here. Approximate sine of 1 using the first two terms of the series for sine of 1. Okay. When we're done with that, we're going to find the maximum error guaranteed by the alternating series error bound when using the first two terms of the series to approximate the sine of 1. Okay. So part A is the sine of 1 is approximately the first term. They want two terms, so that minus that. Okay, so then we can use our calculator, we can approximate that out, and we're going to get 0.8333. Threes are repeating. So then this tells me that the sum of 2, okay, the two-term sum is 0.83 repeating. All right, so what is our error? Our error is going to be less than or equal to the absolute value of the next term in the sequence, in the series, which is this number right here. So that means our error is going to be less than or equal to 1 over 5 factorial, and 1 over 5 factorial is 1 over 120. So that means we're that close to the actual. Okay, I'll write it over here. This means that adding, and instead of writing it out, I'll just show it to you. This means that adding only the first two terms, we are able to approximate the sine of 1 to within that close of the actual. So that is the error that we have, 1 over 120. Okay? So that is the alternating series test with some error, alternating series error bound. And if you have any questions about this, let me know, and we will continue on the next video next.